I'm a little too short for this. Hello, my name's Jesse. We're from WashU Satellite. I'm the chief systems engineer.
And my name is Oliver. I'm the chief mechanical engineer.
Yeah, so I can't see the screen. Sorry, I'm gonna adjust this so that I can see the screen. Can I do this? Screw it, I don't know. Whatever. Yeah, so we're here to show you our systems engineering practices through magnetorquer-based CubeSat development. Before I jump right into our spacecraft design, I'm going to go over why this project is so interesting. So we're trying to do 3D axis control with just magnetorquers, and that is not as trivial as people might think, is because torque is generated when the magnetorquer is perpendicular to the Earth's magnetic field. And if you have 3 magnetorquers, one of them is always going to be aligned with the magnetic field. So we're effectively always going to have one axis of magnetorquer that is uncontrollable. And SCALAR is operating under this fundamental constraint. So what's SCALAR? SCALAR is WashU Satellite's first CubeSat. WashU Satellite's pretty new, and we hope SCALAR could give us experience and flight heritage that we need for future spacecraft projects. It's a 1U CubeSat. We have an embedded magnetorquer board that is fully student designed. Yeah, and there are other restrictions that we had to work around besides the technical constraints that I've mentioned earlier. It's that because we wanted to make this happen as quick as possible, we were restricted by lead time and also restricted by budget, which means that we don't have a GPS or sun sensor, star trackers, etc. But that is why SCALAR is so interesting, is because we have to work around those constraints and we have to come up with creative ways to do that. So SCALAR was designed so that we can give students the experience and we can have flight heritage. Naturally, our mission is pretty simple, is to demonstrate established communication and controls to determine the TRL of club engineering magnetorquers. Our mission objectives is demonstrate WashU Satellite's capability of launching spacecraft and establish effective means and procedure for future satellite projects. And because we happen to have an embedded torquer that is student built, we thought that, let's make this interesting instead of just a beepsat. We can also validate if magnetorquer only control can be achieved in 3D attitude. This is the hardware payload board we have designed, and just for the interest of time, we're not going to go into the details of it, but there is the torquer rod that we have wrapped with a tensioner, and those two are on the top, as you can see. And there is a embedded torquer. The reason being is because it's a 1U. We did not have space to shove 3 rods onto our spacecraft, which we were forced to come up with ways to shove a 3rd axis magnetorquer, and decided, hey, let's just have coils around a PCB, and surprisingly it works. So now I'm gonna briefly go over the control structure. So we're working with a under-actuated space. This shows the nature of the problem we're working with. So you have the Earth's magnetic field, it's the B vector. And like I said, if it's aligned to the Earth's magnetic field, the torquer, if those are aligned, you can't control it at all, you can't generate any torque. So naturally, our control authority lives only on the plane of that normal vector. At any instant, the controller is going to have 2 degrees of freedom, and the subspace is going to rotate as the spacecraft orbits. So we came up with 3 big steps to mitigate this problem. Is that 1, we're going to estimate the current state we have with the sensors we have. We're going to then get the error between the estimated state and our desired state. and project our desired input onto the controllable subspace. So how are we going to estimate the full 3D state? Because we don't have any means to do direct attitude measurement, we have to reconstruct these from the sensors we have, which are a gyroscope, an IMU, magnetometers, and 6 photodiodes, one on each side. Using the photodiodes, we plan to either fully reconstruct the sun vector, or we can just use the values that we get from the photodiodes. We're still exploring how we're going to do that. But with a gyroscope, we hope that we can get the reference state, and with those sensors, we're going to get the error state, which will give us an estimation of where the spacecraft is currently pointing. And this will have to be, of course, reiterated every time step. And now we have an estimation of our attitude. We can now calculate the attitude error. And using the current state, the error of the attitude and the magnetic field of the body frame of the magnetic field, we can calculate the optimal magnetic moment M that would reduce the error that we will have under the current limitations we have. And the point here of the controls logic is that we want this to be able to naturally adapt to the constraints that we are dealing with, which is an underactuated space. Once we do that, we will hopefully get the desired tau, and we will also have to recompute this every time step because the controllable plane will be rotating with the field as it orbits. And the tau we will be getting right out after the controls algorithm will be still in 3D space, which, because our controllable plane is 2D, we'll have to find a way to just project onto a controllable subspace, which that's the animation of how it would look like. So we have the tau, which is our desired pointing tau that will hopefully fix our pointing error. And there's the B field. And of course, there are vector components that align with the B field and will have to be projected onto the control subspace, which gives us tau command. And so with that, we should be able to calculate our magnetic dipole moment that we can directly input, translate be able to command our magnetorquers. Okay, this sounds all lovely and great, but there's one caveat. It's that this only works if our assumptions are true. Like, assumptions, we mean that, for example, like, we know the magnetic field B. Okay, but if B is wrong, we're solving the controls problem in the wrong plane. Or another assumption we can make is that the system produces the magnetic moment that we command. Okay, but if the produced M is not what we command, then we're applying the wrong torque. The bottom line here is this controller is only correct if the system matches its assumptions. So how do we make sure our assumptions are verified?
Yeah, so we're in a challenge now where we have limits on our hardware, and controls moves out of a hardware problem, even a software problem, into a problem of team structure to make sure our assumptions are accurate. So the answer to this question, systems engineering. As a brief overview of our team's structure, we follow, wrong slide. If we simplify our assumptions, if we make it easy for people to ask questions and to update designs as they change, we can have more accurate assumptions and make sure that our model is as good as it can be when we're working with limited data. So we use a responsible engineering model where on a project level, we have project manager, systems engineering lead. Then we divide that project into several modules, which each have responsible engineers. And those modules are divided into components, which each have a point of contact. Now, the interfaces between these is really where the big assumptions happen. So we have direct responsibility for those interfaces, with the systems integration lead making sure each module fits into the project and those assumptions stay up to date, and responsible engineers making sure that each component of their module works well together and has up-to-date connections. Notably, we don't divide up our projects by discipline, so chief engineers are somewhere off to the side working with everybody else. So here's an example for SCALAR. We have our systems engineering lead and project manager helping divide the project into all of these different modules you see here. We have a systems integration lead working to make sure all of those modules work together. We have let's take an example, responsible engineer for structures. I'm biased being a mechie. And we have all of these different points of contact for each kind of part of structures. We can divide it up. And the advantage is that every member of our team is responsible for something real. Even if you're a new member, you can be the point of contact for choosing fasteners, the point of contact for doing one type of testing, and you really feel like you own a part, and each of our members has something tangible. When we go to space, they can say, I did that. It's easy to know who to ask questions to. You can always talk to your responsible engineer, or if you are a responsible engineer, you can talk to the systems integration lead. There's no big question of who do I talk to, who do I ask this question to? And there's clear responsibility for the interfaces between parts. So where this comes in helpful is when people have questions. Let's take an example. If we want to know what angular acceleration can the magnetorquers produce. So our point of contact for the ADCS team, he can just talk to his responsible engineer. It's easy to know who to ask questions to. That responsible engineer can go and talk to the structures team and ask, hey, can you find out the moment of inertia? And now we can have both the responsible engineer for payload go and ask the magnetorquer team, how much power do the magnetorquers have? And then the responsible engineer for structures can ask the structure, hey, what's our moment of inertia? You have that CAD model. And we can mark all of those down as testable criteria that we can update as we go on with the project. That way we don't work off of any outdated assumptions. So as far as verification goes, really I'd say our best way to do this is through design reviews. We mark down each of these testable criteria we find when people have questions that their project relies on. And through our 3 steps of design reviews and all the kind of mini steps in between, we'll make sure that whatever assumptions you're making in your design are up to date with the latest data from the other teams. And so through this, we're able to get the up-to-date assumptions we need for 3-axis control, and we can avoid running into the traps where you might be working off outdated data or working off incorrect assumptions. So the future of SCALAR, as our colleague showed yesterday, is that we're learning how to build these systems engineering models, how to make good assumptions, and really just how to build a CubeSat. This is our first satellite. And then we have another project, ERIS, which is doing research on gamma ray bursts, developing algorithms, working with optics. And so we hope to combine this 1U project and the research balloon and make our 6U vector, which is a much more advanced craft. So we're really taking this experience with a 1U to try and develop all of the best practices to make sure we can do a very ambitious project in the future. Thank you.